Hi, this is Saud. This is about fabricating a classic homemade PLC device using basic equipment and simplified process. We are going to use this type of board, perf board. This board is very practical for the project and circuit design and scale which we are intended to build. Simply with this board we need just to use the jumper wire to link the components to each other. So you insert the component anywhere in the circuit and use the jumper wire to link the pins. This circuit can be built also using a strip board. A strip board is a board with parallel copper traces. So you insert the component, then you will need to cut the copper tracks to isolate the unwanted connections. The difference to the perf board, with the perf board we have the copper dots or pads isolated from each other. That's why you'll need either the jumper wire to connect point to point, or you can even use a solder. So you just keep soldering every pad with the adjacent one to create the connection. There is a way also where you can just insert the components and use the component leg itself and pins to link them together. The advanced way to do this is to use the home-made etched board, where you print the circuit on the copper board itself and use the etching solution to remove the unwanted tracks, and then you end up with a circuit like this one. To do it in this way, you will need more complex process. You will need a PCB Design computer application where you will draw the schematic diagram and then convert that to PCB layout like this one, and then you will need to print this PCB layout by using a laser printer, and then transfer that layout to the copper board, and then use the etching solution to remove the unwanted copper tracks, and then, as we mentioned, you will end up with a circuit like this one. First step, we need to prepare drawing or schematic for the circuit to be built. But before proceeding with this, we need to have some sort of general thinking and vision for the device. Then put the practical plan and implementation steps. This is applicable to any other circuit, in fact, not only to this one. In this project, I thought to have a PLC equipped with four digital outputs, one PID control function, 4 analog inputs, and 4 digital inputs. It needs to have also some sort of wireless communication capability. It should also be equipped with 7-segment LED display to display the status of the PLC, plus the serial port to communicate with the user interface and configuration application, and in this case is going to be a terminal window. And the heart of the system is going to be PIC 18F4620 microcontroller from Microchip. Okay, let's start to draw the schematic diagram. As we agree, I'll follow the simple approach to draw the schematic manually on the paper. We will normally need to take the assistance of the data sheet of the ICs which we will use to build the circuit. In our case here, we'll need the data sheet of the PIC microcontroller, as well as the other associated ICs data sheet and the other components if required. You can also make use of any working schematic diagram with you to help you in designing parts of the circuits. Let us say, for example, the serial communication part, or the analog processing signal circuits and things like that. And then from the drawing, once we are done with the drawing, we will make the list of the components we need to purchase. After completion of the drawing, I have made the list of the components which we will need to install, and I have purchased them, as you can see. And then just let's start now. Install all these components on the board and solder them. To do this, I normally keep the drawing in front of me, and I used the highlighter pen to highlight on the drawing whatever loop I have already finished installing it on the board, and this helps to track down what you have completed already all the time. This is the final product. It took for me, in fact, number of days to complete, as I do this on my free time. And normally it is not expected to be 100% correct all the loops from the first time. So you will need to do some verification after you complete the installation of the components. I done number of corrections, in fact, after I have finished the soldering. Few things to be highlighted here. It is always advisable to install the main microcontroller on a socket, as we have done here, as this makes the life easier in case if you want to replace the IC or remove it for programming or such thing. This is 40 pin IC, and it will be really very difficult to unsolder and replace it from the board. For the jumper wires, if you would like, in fact, they can be installed on the top of the board, but of course the board will definitely look different. I found it really better look to put the wires underneath the board, so the installation and the board will look more cleaner and professional. It is also better idea to keep the high voltage components a little bit away from the low voltage part. As in this case, we have the power supply section. We have got the 24 volts feed, the 12 volt regulator and the 5 volt regulator, and I got the 12 volt relays plus the requirement of the 24 volts for the analog input and the analog loops. Then I have the rest of the components 5 volts. So I have laid all the higher voltage in one side, so they're a little bit away from the low voltage part to avoid any generation of spikes and harmonics. I have fabricated a simple enclosure to accommodate the board. So let's install the board inside the enclosure, and we move to the following step, which is programming the microcontroller. Before proceeding with the microcontroller programming, I would like to give some brief description of the hardware so easily you can follow what I'm doing. Here we have the AC to DC adapter. It is providing the 24 volts to the system, and this is the power supply section. We have here the 4 digital outputs relay contact. Here is the PID function connection. Here is the RS232 connector. This is connecting the PLC to the window terminal, which we are going to discuss in a minute. We have here the 4 analog inputs and then the 4 digital inputs. I'm using LEDs to indicate the status of every input that's applicable also to the output side. And this is the RF module, and I'm using the popular microchip controller PIC 16F84A as the decoder IC for the RF output signal. Here the environment is very noisy, and if I directly decode the RF signal directly by using the main microcontroller, that might slow down a little bit the scanning rate of the system, as it will keep interrupting the main routine. That's why the decoder IC will just decode the signal and then give the final output to the main microcontroller. The other reason why I'm using the PIC 16F84 also is to accommodate future enhancements. In fact, here is the 7-segment LED display to display the status of the PLC, as well as we have the running indication LED. This will keep flashing as long the main routine is executing normal. And here we have a little board. This board, in fact, it is handling the programming interface, so it assists the programming application to download the program to the main microcontroller and then reset the microcontroller once the download is completed. I have developed the program after a number of debugging process. I'm using the MPLAB IDE, Integrated Development Environment, to develop the program. It is in C language. So let's just now compile the program and build the project to generate the hex output file, which we will use to download to the microcontroller. So it is building the project. Yeah, it is successfully compiled. So we'll just download the program now to the main microcontroller. So let's open the file. This is the file. We'll just open it. So program, go ahead. So it will download now the program to the main microcontroller, and once it is completed downloaded, it should start and run, and that's what we are going to observe. Yeah, done. Yeah, it is running. So as you can see, it is showing the 7-segment display HE, indicating that the program is running okay without any error. That it means healthy. And the run status LED also is flashing, indicating that the main routine is executing normal. So this is the terminal window emulator I am using as a user interface. It is based on the TerraTerm software. There is a script running at the background displaying the menu. The dynamic data and values, they are being transmitted from the controller to the window. So the main microcontroller, it is the one updating those. So we're going to go through some of these functions. It is displaying the time at the top, and this is the menu. Through this one we can control the PLC and go through the configuration options. We can, for example, restart the PLC from here, so we can reboot the system. For example, let's do that one. Yes, go ahead. So it is restarting the PLC right now. Yeah, it's running. This is the PID faceplate. I have arranged to generate a fixed PV input through a resistor at 43%, just to check the functionality of the PID right now. So I'll increase the set point above the PV. Yeah, so the output is rising. That is proving it is in reverse action. So we will repeat this just to see. Yeah, as the set point go above the PV, the output is rising. So let's put the PID action to direct. Let's reduce the set point now below the PV. It's the other way around. The output is increasing, as you can see. So yeah, the PID is functioning. Okay, I have connected the output to analog input number 1, so you can see it is matching. Output of the PID I have connected to analog number 1. The purpose of that one, that we will need to check the alarm action later on. Both digital input and digital output status is being displayed here. So we can, for example, force the digital output. So let's force them. Yeah, they are coming on and they are being displayed there as well. So I am doing this through the keyboard. So we will just clear the force. Let's clear the outputs. Are they are on now? So I'll just clear them. Yeah, they are okay, clear. I can in fact activate the outputs from the corresponding input as I put the default logic as a straight logic. So activating DI number 1 will activate DO1. Do it for DI2 will activate DO2, and the same for the rest. Let's check the alarm function right now. So as I have mentioned, I have connected the output of the PID to analog number 1 just to check the alarm activation. So I have set the alarm to activate at 80% when the signal is at 80%. So we will put the PID to manual mode. Yeah, it's in manual mode, and then I'll raise the output. So once it is there at 80%, we should get an alarm. The alarm is there. Yeah, so we'll acknowledge. Yeah, the alarm is acknowledged. Let's reduce it so it clear the alarm. So the alarm is also functioning. Let's check the ability to control the digital output through the remote control. We will activate the digital output number 1. Yes, activate it. Deactivate. We'll try again. Activate it. Deactivate it. This is happening through the RF module. This PLC can be used to control a small processor for some home automation application. This is all about the subject, and I hope it was useful. All the best, and thanks